say delicate things on the record. No, of course, one always forgets that it hasn't been turned on yet.
A few weeks ago, I went to a faculty meeting here, and the physics department they'd installed. Ever since COVID, like we used to be all in person, but now everyone wants to have hybrid online faculty meetings, so they can just not pay any attention and sit in their offices and work. They had set up in our faculty meetings like these owl things, those that like the cameras and stuff. And I was just, chatting about like some, voting related thing, and then someone said to me, those owls there, they hear you pretty well. Whatever you're saying, it's like okay, it's good. I did not think about that. Good to know. This is good to know.
Keep your
everyone, who tuned into the faculty meeting in their homes and offices were listening to you.
That's why it's basically right. That's kind of
So we just like 30 seconds. I think Ethan was going to make an announcement, and then he like suddenly ran out.
Yeah, please. Yeah, of course. No.
We probably shouldn't wait.
I guess I didn't say it until you understand.
It's a minute in already.
Oh, yeah. That's not yet.
The other one's an identical play.
Oh, there we go. Success. Am I supposed to do tricks? See if I can keep it in the air.
All right, so is this thing on? Yeah. For the afternoon session, we have gifts for you. So at the end of TASI 2023, they said, we have this soccer ball. Here, give it to TASI 2024. And then at the end of TASI 2024, they say, yeah, now we have 2 soccer balls. Give it to TASI 2025. So for you, from your predecessors, are these soccer balls.
So the question is, what is the sequence? Is it exponential growth of soccer balls?
Don't let me throw it too far.
What's left up?
Do not give us 4 to give to next year.
Just 3.
Oh, is it like
Right.
Without further ado, Nathaniel.
All right, how's everyone doing? Woo! All right, is everyone ready to write down the generalized symmetries of the standard model today?
Yeah.
Woo! Okay, so we are gonna, without further ado, we're just gonna get into it then, because we have a lot of ground to cover, and I think we'll all be happier if we get to the destination. So as a quick reminder, last lecture, we presented the field content of the standard model. Here I'm just reminding you of the fermions. We have ng is equal to 3 generations of these, which under the standard model gauge group. And we recognize that if we turn off the Yukawa couplings in the standard model, we have naively what seems to be a U3 to the 5th global symmetry, under which any one of these, there are 3 of each of them. They're distinguished relative to each other by their standard model quantum numbers, but the 3 copies of each type of field I can rotate into each other and properly preserved by the is a full U3 worth, and so that gives us the U3 to the 5th. And in the spirit of analysis, which permeates all of these lectures, we can ask, of course, the Yukawas break the symmetry. One of the things we'll do today is figure out what we break it down to. But before we do that, you can just ask, okay, what are some appropriate charge assignments to the Yukawas? And of course, you have some freedom when you say that the free fermions, each one of them transforms into U3. You could say it transforms as a fundamental or an anti-fundamental. It doesn't really matter. So it's convention typically for people to define the fermions of the standard model that transform as SU2 doublets, transform the fundamental of their flavor symmetry, and the ones that transform and the anti-fundamental, so that the spurions have this nice sort of bifundamental nature with respect to pairs of these symmetries, right? So the uptype Yukawa, you could say transforms the anti-fundamental of the U3Q symmetry and the fundamental of the U3U, for example, similar with Y down, and then with the lepton Yukawa. Okay. Good. So the first question we have is what is actually the global symmetry structure? And this is one of the great things about Tazi is Hotat and I had the chance to work out our differences last night. So I think I will now give you the consensus view as to what the actual global symmetry is. So the naive picture we said is that it's U3 to the 5th. So I'll put scare quotes around that. If you ask a phenomenologist, what they'll do is they'll tell you, well, you know, really U3 is, I'll put scare quotes here too, phenomenology scare quotes, is SU3 cross U1. This is only locally true. So globally, what we should recognize is if I have a U3 that's acting on these fermions, there is a center. Actually, does everyone feel like they're comfortable with the idea of a center symmetry of SUN? I'd like to be briefly reminded of it. Briefly, good. So the center of a group, right, is the set of group elements that commute with all the other ones. Okay. In the case of SUN, that's going to be all of the group elements that are proportional to the identity, and then satisfying the SU requirement means that they become the nth roots of unity. Okay. So the nth roots of unity multiplying the identity as complex phases. Obviously, if I take the determinant of that thing, I'm going to get 1, and it's going to be unitary. And so the center of SUN is Zn. Okay, so the Zn. The SUN center is Zn. But now you recognize, right, if I have, say, a fermion transforming the fundamental of SU3, if I do a center transformation by the center symmetry, that I take each of the 3 components of the fermion in that space, and I multiply it by some third unity, right? It looks like I could have done each one. Should identify them with each other. Take the quotient by just them. That's what we mean by this quotient. And the fact that in U3 we're acting on, again, these 3-component complex fermions shouldn't double count. Okay, so the phenomenologist often will engage in separate counting of these 2 factors. And in the lecture, it will be somewhat useful by the center, but you keep this in mind in the rest of the discussion. This is what by the flavor symmetry. And so now you can ask, is there any extra, so this is what we mean by the symmetry. Are we double counting any parts of the symmetry group in the standard model? Is this really the whole symmetry, or is this overcounting by some amount? Have we accounted for some of these symmetry transformations elsewhere already? Yeah?
So it's gauged, right?
It's gauged, indeed. So we have U1 hypercharge, right, under which we've assigned all of these fermions different hypercharge quantum numbers. But if I'm telling you that I can rotate all these fermions into each other, okay, there is some U1 subgroup of U3 to the 5th that just corresponds to the charge assignments of U1 hypercharge. So the global part, in some sense, the global symmetry of hypercharge is actually already, is counted for in our gauge symmetries. So I could do a gauge transformation by a constant parameter. That would be the global symmetry part of U1 as far as the fermions are concerned. And so we're double counting it by putting it here. Okay. So properly speaking, we should take the quotient by one hypercharge. Are we done with our double counting? Is there anything else we're double counting?
I'm going to guess yes.
The centers, okay, good. So excellent on both counts. It, however, was a trick question, and this is why I'm indebted to Hotat. And we'll come back to this actually in a very important way about midway through the lecture. So indeed, you could also say, it looks like we're in the spirit of, there was a symmetry transformation that we could do that we'd recognize as a U1 hypercharge transformation that's part of this U through the 5th. You could also say we're entitled to do a center symmetry transformation with respect to the centers of either SU3 or SU2. So just to think about what that would mean, so you can ask, how does a field in a given irrep of SUN transform under a center symmetry transformation? Its charge under the center symmetry transformation is given by what we call its n-ality. You can determine that by just counting the number of Young tableau mod the boxes in its Young tableau mod n. So it's very simple. If you have a fundamental of SUN, then its n-ality is 1. Okay, and so then that means doing a center symmetry transformation, you're taking in this case, a cube root of unity to the power of the n-ality. So that's just the cube root of unity acting on Q. Things of the fundamental, they have opposite sign of that transformation. Or, they're whatever, 2 boxes in the Young tableau. Gives you the second cube root of unity. Okay. That, again, corresponds to what looks like a global symmetry transformation by which we rotate Q by a cubed root of unity and U and D by the second cube root of unity. That also looks like it's part of this U3 to the 5th. And similarly, you could do the same thing for SU2. So SU2 is just the root of unity. Something that has n-ality 1, in other words, the fundamental of SU2 would pick up a minus sign. If we did a center symmetry transformation. So both Q and L would transform by a minus sign. That also looks like it's part of U3 to the 5th. Could we mod out by the quotient of Z3 and Z2? Yes. OK, yes, indeed. And this is what Hotak convinced me of. No. Okay. And a good way to think about it will actually come to you later on in the lecture, because these centers of this play another role midway through the lecture. But the point is actually that those transformations we could also think as being transformations by an appropriately chosen phase of hypercharge. So if I rotation by a sufficiently large hypercharge angle, you'll notice there's a sense in which some of these 6th roots of unity, okay? And so there's actually a subgroup of hypercharge that I could take, which corresponds also either to the Z3 center or the Z2 center, and that transformation would do the same thing, okay? So those transformations with respect to the global symmetry group are already accounted for by the quotient with hypercharge.
So you're suggesting the standard model should have some quotients also in the gauge.
We'll get to halfway through it may or may not. We'll get to that halfway through the lecture. Okay. So indeed, anticipating a little bit of where we're going to go to when we develop the higher form structure of the standard model. But just at the level of the global symmetries, the zero form symmetries of the standard model, that would actually be a double counting in this quotient. And so properly speaking, we're really just going to take the quotient by the global part of hypercharge. OK. So this is, if you wanted to be pedantic and you want to annoy your phenomenologist friends, right, you could ask, what's the global symmetry group of the standard model? They can say U3 to the 5th. You're going to say no. OK. And then you'll win their eternal enmity. OK. Good. So that's the symmetry group. This symmetry group will come back to, so this will play a very interesting and beautiful role, laboring the point. This is not just bookkeeping, so this will play a very important role when we talk about the higher group structure of the standard model, which is an interesting interplay between higher form symmetries of differing degree. So the structure of the symmetry and its anomaly structure, which we'll get to momentarily, will be important. Good. So what happens now when we put the spurions to their background values, right? What happens when we actually break the symmetry? What is the surviving symmetry in the presence of non-vanishing Yukawas? So to analyze that, we can recognize, right, very generically, each one of these is a 3x3 complex matrix. Once we recognize that we have the freedom to do U3 transformations, for example, of the fermions that appear in the Yukawas, we can use a U3 transformation of each one of those fermions. Those are 2 unitary transformations, and so we can use that to, of course, diagonalize these 3x3 complex matrices, right? So very naively, for example, if I were to use the transformations of the leptons, so the U3L and the U3E transformations to diagonalize the electron type Yukawas, that would give me some diagonal matrix. And the only symmetries that are left over in the presence of that diagonal matrix, the entries are not equal. We know that because the diagonal Yukawa is multiplied by the Higgs vev, large lepton masses. The fact that the electron and the muon and the tau have different masses tells us the diagonal entries are not equal. And so that means the residual symmetry that's preserved by that diagonal matrix is just going to be 3 different U1 factors. So those are the U1 factors where each generation of each of these fermions rotates in compensating ways. Okay? Good. So non-zero electron type Yukawas, this is going to break the U3L cross U3E down to a U1, we'll call this capital L sub E, a U1 capital L sub mu, and a U1 capital L sub tau. Capital L here is just meant to denote lepton. There's, of course, a diagonal lepton number that we will care about later, but this is just the statement that there's, at this point, a separate one for each of the 3 generations of charged lepton. Okay. We can repeat the exercise, board again, for y up and y down. Okay, so very naively, this again breaks it to now you could say this is, say, up quark number, charm quark number, and top quark number for the up type Yukawas. And for the down type Yukawas, you might naively think you again get 3 U1s. And I've used the word naively repeatedly to suggest that I'm making a mistake. What mistake have I made? By imagining that I can use the transformation works to diagonalize both of these matrices and therefore preserve these 6 U1s. Yeah. I've used U through Q twice, that's right. Yeah. So in other words, these are both general complex matrices. Let's say I pick the specific form of the U through Q transformation here to diagonalize YU. I do not have the freedom to make a separate U through Q transformation here. It acts on both of them. So if I did a different transformation here, it would undo whatever I'd done here. So I only have one set of transformations that I get to do. So how bad the consequence of that is, so of course, if these matrices commuted, then I would be free to do that, right? I could simultaneously diagonalize them by the same set of transformations. But again, the observation is in nature they don't commute. And so the fact that they don't commute means of this 6 set of U1s, in fact, all I'm left with is 1. So all of these boil down to a single U1, which we'll call U1 baryon number. And U1 baryon basically says in all of these things, you rotate each of the generations of Q in one direction, and the U's and the D's in the compensating direction, and you rotate everyone by the same amount, so it's a single U1's worth. And so that is what we'd identify as baryon number. In particular, if we've appropriately scaled it relative to these quark charge assignments, protons, for example, would have baryon number +1, and antiprotons would have baryon number -1. All right. Good. So it looks like the unbroken symmetry is we have 3 lepton numbers, okay? And we have 1 baryon number. Have I overcounted anything here? Any guesses? 50-50 chance, yes or no? Yeah, no, you don't count. You get the Van hammer. Yes?
Isn't the lepton number not actually conserved independently because of the neutrino loss?
Good. So, okay. There's a whole other thing we've done here, but right now we're playing by the very rigid rule of the standard model. We're saying, given the symmetries I've written down and the marginal relevant interactions, these are symmetries. You have made the wonderful observation that at no point did we write down a neutrino mass. That's, of course, a standard model. We'll get to that soon. But let's take for a moment, let's imagine we live in the 1960s world where the neutrinos could be massless. This would be an okay symmetry. But just by the rules of the game, is this global symmetry, are we double counting anything? So we still have the gauge symmetries. Is there anything in the gauge symmetry that might look like any of the symmetries we've written down here? I will emphasize, sorry? No, so SU2 no longer, so that good, the center of SU2 doesn't play a role, but the center of SU3 plays a role. The center of SU3 plays a role because the surviving baryon number, remember I told you, in each of these you have, so you have the Q's and the U's and the D's. The baryon number corresponds to rotating each of the q's, the 3 generations of q, in the same direction, and compensating by rotating the u's and the d's in the opposite direction. So in some sense, baryon number is proportional to u1q minus u1u minus u1d. That looks like a center symmetry transformation of SU3, right? Where we multiply, where q as a fundamental and u's and the d's as anti-fundamentals rotate in the opposite directions with respect to the center symmetry transformation. Equivalently, we could have chosen a very special phase of a U1 transformation that's it corresponds to the same transformation as the center of SU3. And so we recognize we're overcounting this by a Z3. OK.
So just to make sure I understand, that Z3 is what's left of the U1 in the denominator there?
Yes, which the U1 includes all of hypercharge plus the parts of the U1 that overlap with the centers of SU3 and SU2. Here, you could say this is the diagonal. You could either think of it as the center of SU3 or the Z3 subgroup of hypercharge. Right, those are equivalent. Good. OK, so those are the unbroken symmetries. This is briefly about spurion analysis. So on my first lecture, I mentioned one of the motivations for conformal technicolor was the idea that you wanted the scaling dimension of H dagger H to be close to 4, but you wanted the scaling dimension of H to be close to 1. So the former consideration was designed to understand why the Higgs mass could be small as a result of some sort of dimensional transmutation. And the latter was because you wanted the flavor structure of the standard model to dominate the interactions between fermions, which is consistent with data. And that is something that's very much enforced upon you by thinking about the spurion analysis here. So if you actually look in nature, once you've diagonalized these Yukawas, there is one large component of the Yukawas. So the top Yukawa coupling is about 1. All right, the next largest one is the bottom type Yukawa, the sort of element here, dramatically smaller. And all of the surviving mixing angles, right, that correspond to the fact that I can't mutually diagonalize everybody, that these matrices don't commute, those are progressively smaller and smaller between different generations. And so that is to say, there's a very hierarchical structure of flavor in the standard model. And so if you want to understand, make predictions in the standard model for some process you're measuring of some decays of B mesons and other standard model fermions, the patterns that those follow are very naturally governed by the spurion analysis here. That low powers of the Yukawas pick out the directions of symmetry breaking that dominate, and that corresponds to what we see in nature. So this is just to say, the hierarchies that are present in the Yukawas make spurion analysis a good idea, and you can use spurion analysis to understand pretty much all of flavor physics. Good. I'm going to leave something in the notes, some more details about what you can do with these structures, but we have to get ourselves to higher group symmetries, so I'm going to proceed apace then. All right. Are these good quantum symmetries of the theory? They're good classical symmetries of the theory. Yeah, so they're not good quantum, they're not uniformly good quantum symmetries of the theory. Right, so as we know, classical apparent theory symmetries of your classical action can fail to be symmetries of the quantum theory. There are various ways to say it. The phenomenologists say, well, you can have a global symmetry. Some fermions are coupled, and now there are triangle diagrams to which you can attach various gauge bosons. And what you find from the fact that the insertion of a global symmetry current converts itself into gauge bosons is that what would classically have been some conserved global symmetry current now is proportional to some anomaly coefficient, which depends on the number and representations of these fermions. There's just some coefficient, which, depending on how you normalize it, can be something of the order of 16 or 32 pi squared. And then this is proportional to the appropriate FF dual of whatever gauge fields participate in this anomaly. Now, this is how the phenomenologist would describe it. This is very unilluminating, right? If we say that an anomaly is an example of a classical symmetry which is viable quantum mechanically, there should be a deeper way of seeing it. And indeed, Fujikawa gave us a very nice way of understanding it, that the thing in the path integral could be non-invariant under a classical transformation is the measure of the fermions. And so you could equivalently derive this relation by studying the variation of the measure of the fermions with respect to a global symmetry transformation. Okay, so there are situations where classical symmetries are violated quantum mechanically. Now, if this were a gauge symmetry, we would have a pathology of the theory, right? We'd have an anomalous gauge symmetry, and all sorts of terrible things would happen. The standard model has no gauge anomalies, okay, where there are 3 gauge currents inserted in these diagrams. But its global symmetries do have ABJ anomalies, and those are, there's nothing sick about it. It's just a very beautiful consequence of quantum mechanics. Good. So we can ask, indeed, are these global symmetries anomalous? These days, the parlance, if you have an anomaly of a global symmetry with respect to 2 gauge currents, we typically call this an ABJ anomaly after Adler, Bell, and Jakif. It's also often called a chiral anomaly. I'll just typically call these ABJ anomalies in these lectures. And so it's useful to ask the question, do we have ABJ anomalies of these global symmetries? Indeed, we do. So it turns out there are, if you take, in general, many of these symmetries. So an anomaly involves 1 insertion of a global symmetry current and 2 insertions of gauge currents. So typically, the things that will have ABJ anomalies are abelian parts of the global symmetry, so various U1 factors. Okay. If I took a non-abelian piece, typically, since the trace of that would vanish. So typically, the ABJ anomalies are abelian parts of the global symmetry with respect to 2 SU3 currents or 2 SU2 currents or 2 hypercharged currents. I've enumerated all of the interesting ABJ anomalies in the lecture notes. In the interest of time, I'm just going to zoom in on 2 that matter in some sense the most for the theory of nature. So as we've written it, right, we have the U1 baryon number, and then we have these 3 lepton numbers. It's conventional to decompose these rather than writing them as 1 for each generation of charged leptons. Typically, it's more convenient to say there's 1 uniform U1 lepton number in which we rotate all 3 generations by the same amount. And then we could account for the rest of the symmetries by looking, for example, at differences in leptons between generations. Okay. Now, these are all going to die a horrible death when we write down neutrino masses. So I'm not going to worry about them too much. But this could plausibly also be global symmetry. And so we should care about its anomaly. So it turns out, so if you had to guess, so U1 lepton number could have anomalies with respect to any. Which one does it have anomalies with respect to? Does it have anomalies with respect to SU3? No, why not? There's nothing, yeah. So in order to get an anomaly in these triangle diagrams, it depends on the quantum numbers of the fermions running in the loop. Lepton number, the only things charged under lepton number are the leptons. Those are under SU3. So thankfully, lepton number has no SU3 ABJ anomaly. Does baryon number have an SU3 ABJ anomaly? No, why not? Good, okay. Equivalently, when you do the accounting for the first group, you have the cubes. Those are fundamental when you treat SU2 as a global symmetry, right? Then you have the U's and the anti-fundamentals. They contribute to the anomaly in the opposite direction. So indeed, the SU3 anomaly cancels, right? There are 2 of them, okay? However, both of these have symmetries with respect to SU2 and charge. And so the accounting of the anomaly coefficients, there is both a hypercharge. So again, as an ABJ anomaly, it would be 1 factor of the global symmetry, 2 factors of the gauge symmetry. Okay, so baryon with respect to hypercharge, it depends on the number of generations. So if I only had 1 generation, it would be -1/2 in our conventions. I have 3 generations, so I'll keep number of generations here. Lepton number is the same. With respect to SU2, the sign is opposite, and there's a factor of 2, but they're both proportional to just the number of generations. Okay. And so from this exercise, we can see that rather than talking about U1 baryon number and U1 lepton number, each of them appears to have ABJ anomalies with electroweak gauge group. Instead, it would be productive to think about the combinations of baryon plus lepton number and baryon minus lepton number. Okay, so U1 baryon minus lepton number. Does this have an ABJ anomaly with respect to the electroweak group? No, right. And the reason for that is just that because these have equal anomalies, the difference, the anomaly coefficients will cancel. Okay, so this is anomaly free. And then the other linear combination, baryon plus lepton number, does this have an anomaly? Yes, right. So now I'm just adding these, and that's just making the anomaly worse. Right. Okay, so this has an ABJ anomaly. But the interesting thing is, okay, so we can ask what are the consequences of having this ABJ anomaly? We're going to set aside right now the ABJ anomaly with respect to hypercharge. As Clay will start to tell you on Friday, that ABJ anomaly means that, properly speaking, the U1 baryon plus lepton number, you could think of it as becoming a non-invertible symmetry. So we'll develop that more later this week. But if you have the anomaly with respect to FG2 left, that just is a breaking of the symmetry down to some discrete subgroup. There is, however, a surviving discrete subgroup. So if I have an anomalous global symmetry, I imagine trying to do a global symmetry transformation, I could think about, again, in the Fujikawa language, the variation of the fermionic measure gives me some change in the action. That's the manifestation of the anomaly. And so very generally, if I do a transformation of an anomalous global symmetry by some angle alpha, the action will vary proportional to alpha itself, whatever the anomaly coefficient is. And then the integral of whatever this F dual term is, which you may or may not recognize as a Chern-Podragon density, which takes on integer values. Okay, so this is some integer valued quantity. If this particularly is a non-abelian gauge group. Okay, so with respect to SU2, then in general this is an integer valued quantity. But now that means there is a surviving discrete subgroup of my original U1 baryon plus lepton number. I can choose special values of my rotation parameter so that the overall variation in the action is proportional to 2 pi times some integer. And then I will just be changing the path integral by 2 pi I times some integer. Okay. So indeed, the symmetry is preserved. For angles, alpha is 2 pi times some integer k over the anomaly coefficient. Okay. So in the case of baryon plus lepton number, what survives the SU2 anomaly properly normalized is just z number of generations subgroup of baryon plus lepton number. That's what survives the anomaly. Okay. So the anomaly-free global symmetry of the standard model with the Yukawa turned on is U1 baryon minus lepton number cross this Z3 subgroup, where I'm just going to write it as the number of generations to remind you that if we lived in a universe with 1 generation or 2 generations of fermions, it would actually have dramatically different implications for the fate of baryon number. Okay. In particular, the fact that this is a Z3 means that even though I violate baryon plus lepton number, processes in the standard model that might do it, they have to preserve, they can only violate baryon number by 3 units, okay? And so you expect that there are processes in which, so baryon number could be violated by 3 units, and the fact that baryon minus lepton number is a good symmetry means lepton number is also violated by 3 units.
What's that 1 unit of baryon number in your convention? A quark?
No, so baryon I'm defining as 1/3 the U1Q minus U1D minus U1U, so that protons have baryon number 1. Okay. Now, it's not at all obvious. There's, in some sense, this is the what is allowed by the surviving symmetries of the standard model even after the anomaly. And you can ask yourself, are there processes in nature that do this? And the answer is absolutely. So if we take the standard model at finite temperature, we take Luca seriously, then there are finite temperature analogons of instantons called sphalerons, which in fact are sensitive to the anomaly.
Analogons?
Yes. That also sounds like a particle, but it's not the word. Good. That mediate baryon and lepton number violation by 3 units. Okay. In fact, there's something much more interesting, which we'll come back to at the end of today's lecture, which is if I plop a monopole into the standard model that's charged under hypercharge, and as we'll see, if I try to scatter fermions off of it, scattering of fermions off of that monopole is guaranteed to violate baryon and lepton number precisely by this much. So if there are monopoles in the universe, actually we should go about looking for them by looking for these sorts of processes catalyzed by monopoles sitting, for example, in the sun and other stars. Yeah?
What happened to the mod Z3 upstairs?
That did not do anything productive with respect to, so that's just saying it's a double counting, right? It's just that there's a U1 baryon transformation that you would have thought you could have made, which actually is already counted in a centered transformation of SU3C. But that doesn't do anything with respect to controlling the surviving subgroup of B plus L. Okay. Okay, so I just want to highlight this to you. This is a very underappreciated fact that although the classical symmetries of the standard model protect both baryon and lepton number just as accidental symmetries. In other words, we can't write down marginal and relevant operators that violate it. Quantum mechanically, they're broken, but they're still broken entirely, but instead to some interesting subgroup that although it allows baryon and lepton number violation, forces it to be by some number of units that are actually sensitive to the number of generations of fermions in the standard model. And this is a dramatically underappreciated fact. But if you want to look from the standard model in the IR up into the UV, this is telling you that this is something that's very interesting to probe. Yeah?
It's really embarrassing by how little I know about experiment. But just to confirm, we haven't seen any baryon.
We haven't seen, that's right, delta B of any number. What we mostly look for is delta B is equal to 1 processes, right, which would be proton decay, okay? This is something much more dramatic. This would say, for example, helium nuclei explode, right, into lepton, okay? But for example, if you parked a monopole in the middle of the sun, it would be doing that in the sun's core with some frequency. And you could, for example, look for the neutrinos that came from that process. We actually currently do that for delta B is equal to 1 processes. So the Super Kame-Kande experiment places bounds on monopoles parked in the sun under the assumption that they do something more violent. But what I'm telling you is there's no guarantee they do that very violent thing. But as we'll develop at the very end of the lecture, it's forced upon you that if you have a monopole with a hypercharge field configuration, it will always catalyze processes of this form, just given the anomaly structure of the standard model.
So if the standard model itself, this is the only symmetry, why don't more people look for processes?
I think people don't appreciate, we'll get to it in a second. I think I'm going to argue that actually the modern language of generalized symmetries makes the importance of these processes much more obvious than they ever had been before. Okay, 2 questions. Sorry.
I'm a little confused because we seem to be talking about processes that would have a delta B of 1 as not being likely to see these specific processes that have a delta B of 3. Would the delta B of 1 catch the delta B of 3?
Good. So if we're thinking about what Super Kame-Kande is looking for, the answer is no. Because the reason for it is the reason Super Kame-Kande sets a limit. That's a great question. We're going down a good rabbit hole. What they're actually looking for is that the idea is the monopole is parked in the sun. It's causing protons to decay. One of the things they decay into is a neutrino. And it's looking for what are basically monoenergetic neutrinos from the monopoles that would be parked in the sun. Okay. And so you have, of course, Super K sees lots of neutrinos. But what it really does is does an analysis, being looking for a peak corresponding to whatever the expected phase space distribution of the neutrinos is from the monopole catalyzed decay. Whereas if you had a delta B is equal to 3 process, okay, one thing is the rate is dramatically lower because now all you can do, for example, is explode helium nuclei, right? You're not going to get 3 free baryons anytime soon to come together. But you could, if you crossed monopole across the helium nucleus, catalyze these processes. But it would make several neutrinos. And so that would smear out the phase space distribution. And so basically it falls out of the acceptance of research. Okay. It's a great question.
Can you say again what monopole we're talking about?
charged under what?
Good. So I'll get to that. Actually, it will become much more clear when we get to the end of the lecture and we develop the two-group structure of the standard model. So if you're willing to wait till the end of the lecture, we'll get back to it then. And there was one more question? Yeah.
Like, how does this change if there was like another generation that was just really heavy? So we just have to see.
Good. So we actually know no asterisk up to the phenomenon of symmetric mass generation. We know that there cannot be a fourth generation that acquires its mass from the Higgs, like the other three generations. The reason that was a totally viable possibility until the discovery of the Higgs boson in 2012. They just could have been outside of experimental reach. But a very heavy set of fermions, they have very large couplings to the Higgs boson, and that would lead to extremely large modifications to the Higgs couplings to photons and gluons, which are loop-induced processes. And so the fact that we started to see Higgs couplings to photons and gluons that were bang on the standard model allowed us to rule out a fourth generation of chiral standard model fermions. Yeah. Great questions. All right. OK. Good. We're actually in a good position now. I told you we would come back to the theta angles of the standard model, right? So I told you normally everyone writes down the theta angle for SU3, but they suppress theta angles for SU2 and hypercharge. We can now come back to recognize that that is slightly premature. Good. So the fate of theta 2, OK, what we would normally say is, well, we do know that baryon plus lepton number has an ABJ anomaly with respect to SU2 left, okay? And so that means if we do a U1B plus L transformation, that means I'm going to shift the action by an amount proportional that looks like this, where these are now the SU2 gauge field strengths and their duals. So this has the effect of changing what you would call the coefficient of the SU2 theta term, okay? But we know that U1B plus L is a good symmetry of the standard model, which means it doesn't, if we do this transformation, none of the other terms in the standard model Lagrangian change. So the only thing that changes is the theta angle of SU2. And that means we have the freedom to set it to 0 without changing anything else. Or equivalently, it's unphysical. So that's what we use to discard the theta angle of SU2. So we'd say unphysical because of the U1 B plus L SU2 left squared anomaly. Quick question. Why doesn't this also kill the theta parameter of SU3? Why don't I just kill the QCD theta parameter that way? Good. The good global symmetries of the standard model didn't have an anomaly with respect to SU3. Now, there are lots of other global symmetries that are broken by the Yukawas. But if I did a transformation by them, sure, they would change the SU3 theta angle, but they would also change phases. They would have effects, physically observable effects, in terms of changing measurable phases in the Yukawas. They would change something else in the Lagrangian. And so what that means is because the symmetries, the global symmetries that have SU3 anomalies, are broken by the Yukawa couplings, that although I can use that to change what I call the theta parameter of QCD, what I'm really doing is swapping phases in the Yukawas with the theta parameter. So it becomes physical. There's a combination is invariant under those transformations, which is measurable. So that's why that survives. Very good. OK, so that's why the logic only works for SU2, because this was otherwise a good symmetry of the Lagrangian. Now, hypercharge, you could have said the same thing. We actually discard it really before we even come to this rationale, because as we've noted, abelian gauge theories have trivial topology in flat space. There's no instant-time configurations. And so the theta term for hypercharge really is just a total derivative that I can discard the boundary term for. OK, so that's normally why we discard it. But I want to hopefully convince you that this argument is somewhat flawed, right? This assumes that the standard model is just these perturbative, local particle degrees of freedom living in flat space. If space-time had any interesting other topology, this conclusion would change. And in particular, something that would change it is if we sat a monopole anywhere in the universe. Then if I were to attempt to get rid of this as a boundary term, I would actually be sensitive to the fact that the monopole in some sense creates a boundary for hypercharge. Putting it a different way, as many of you may know, there's something called the Witten effect. The Witten effect is the idea that if I have a monopole with respect to, say, a U1 gauge theory, and that U1 gauge theory has a theta angle, the monopole actually becomes a dion. It acquires an electrical charge that's proportional to the theta parameter. Now, we don't have a great deal of time in these lectures to go into the Witten effect, but it's just to tell you, if I have a monopole in my theory, the theta angle, even of abelian gauge theories, becomes physical. And we can have a superabundance of monopoles sitting out there in the universe. And if we did, as soon as we measured the spectrum, the charges of even one of them, we would immediately become sensitive to abelian theta angles. So the standard model, we should absolutely think of it as having some theta parameter that we are sensitive to in the spectrum of monopoles. Okay? So if we don't discard this because of total derivatives, now you would say, well, Professor Craig, we're still discarding it because we can rotate it away, right? But now there's a catch. If I haven't discarded this as a total derivative, of course I can change each of these by doing a B plus L transformation. But one B plus L transformation changes both of these in correlated ways, right? So in particular, if I imagined doing a single B plus L transformation, theta 2 would go to, say, theta 2 plus whatever the anomaly coefficient was, number of generations, times whatever the rotation was, and theta hypercharge would go to minus the number of generations over 2 times that rotation, right? But of course, that means that the linear combination theta 2 plus 2 theta hypercharge is not changed by this anomalous rotation. And so this cannot be set to 0, and this is physical. And this makes enormous sense, because if you take the standard model and you break electric symmetry, we know at low energies that's going to give us electromagnetism. And there's going to be a linear combination of the SU2 theta term and the hypercharged theta term that you would call the electromagnetic theta term. It's precisely this linear combination, as it must be, because once we've descended to low energies and we're just asking about the standard model charge spectrum with respect to electromagnetism, the fermions are all vector-like, so they don't have an anomaly. And that means there's no anomaly we could use to try to get rid of this. Okay, so this is both physical in this, you could imagine in the UV, but it very much also descends to the theta angle of electromagnetism. And if in our professional lifetimes we find a monopole somewhere out there, we can go ahead and measure this, because then we'll be adding something new to our description of nature as particle physics. Okay, fantastic. These are not the only anomalies I want to talk about. I want to talk about one more set of anomalies. Then I want to talk about some global symmetries of the Higgs, a little bit of higher, I just want to invoke higher spin symmetry, and then we'll do the generalized symmetries of the standard model. How many people have heard of 't Hooft anomalies? Okay, all right, good. So I'm going to do, for the benefit of everybody, I'll do a lightning review of a 't Hooft anomaly in contrast to an ABJ anomaly. And we'll talk about this in the context of the standard model, but this will play a very important role when we discuss the generalized symmetry structure of the standard model. So what are 't Hooft anomalies? 't Hooft anomalies are a stroke of genius. I don't know how else to put it. They're not genuine forms of symmetry breaking like the ABJ anomaly. 't Hooft anomalies you could think of them as situations where maybe I have some fermions transforming into a global symmetry, and I could write down a triangle diagram, either one that has just 3 global current insertions, so no gauge bosons attached to it, or it could have 2 global symmetry insertions and just 1 gauge current attached to it. And either way, there's no sort of gauge field density on the right-hand side that would give me non-conformation of my global symmetry. Okay, so I still have a global symmetry whose current is conserved, but this existence of these diagrams now gives rise to a very powerful thought experiment. Okay, the powerful thought experiment to distinguish, that we can allow us to distinguish between theories, global symmetries that have a 't Hooft anomaly or don't, is we could just imagine gauging the global symmetry, right? So in modern parlance, we would say we would couple background gauge fields to the global current. In other words, So we would just imagine adding to the action some piece, for example, in 4 dimensions. You know, it is what it says on the box, right? You had your global symmetry current, you attach a gauge boson to it. This, of course, is what we would call normal gauge currents in the standard model. We've attached a gauge boson to a global symmetry current of the matter. But the thing that we're doing is we're imagining, in the path integral, when we say it's a background gauge field, that means we're not integrating over it, right, in our sum over paths. And so in some sense, we should think of the path integral as being a function of the value of the background gauge field. Equivalently, it's just a classical source term that we're turning on to create some of these global symmetry currents. Okay. So that's just a reminder that all we do is we integrate over the actual fields of the theory and not the background gauge fields. Okay, so why is this a useful exercise? Well, if we turn on the background gauge fields, now that transmogrifies these triangle diagrams, right? Now they become, and I'll draw them, actually, this is what colored Haguroma is for, right? Does anyone have a preferred color? Just so I have synesthesia. I don't know if anyone knows what that is. It's where numbers have colors. Okay. Yeah, to synesthesia, all right. Does background gauge field have a color for anyone? Your options are blue, red, or yellow. Yellow, okay. Background gauge fields are yellow. Okay. Great, okay, so now we've coupled these background gauge fields. Now, of course, they're, with respect to the gauge transformations of the background gauge fields, we've turned on or activated actual gauge anomalies, not just ABJ anomalies, but potentially real gauge anomalies. Okay. So one sign, one indication of this is these are global symmetries that possess an insuperable abstraction to gauging. Right? There is something in the theory where if we tried to couple real gauge bosons to them, we would find there's a pathology in the theory. But even without actually that obstruction is not just a disappointment, but it's actually a piece of information that we can carry with us. Because even just treating these as background gauge fields, the existence of these anomalies is a renormalization group invariant. And so these anomalies exist and are conserved as a function of scale in our theories. And that means we should be able to match them, for example, between the ultraviolet and the infrared. And this is what 't Hooft had in mind originally when he came up with the idea of 't Hooft anomalies and 't Hooft anomaly matching. He, of course, was thinking about QCD. And the basic idea is, as a function of energy scale, so the way that 't Hooft thought about it was not so much in our modern language of background gauge fields. He actually had the idea that, as an experimentalist, how do you really know the difference between a global symmetry and a very, very weakly gauged gauge symmetry, right, with a tiny, tiny gauge coupling? Okay, there's that's an extremely weak long-range force. You would never be sensitive to it, so you don't know the difference. So you might as well imagine that, in fact, the global symmetry is very weakly gauged. And so you'd say, let's imagine I have some actual physical fields in my theory that contribute to a 't Hooft anomaly. Okay, so they have some anomaly coefficient A. And maybe there is some incredibly complicated dynamics in the theory. Maybe in addition to global symmetries, there's other gauge dynamics like in QCD, where the UV degrees of freedom get dramatically rearranged in the IR, and there's some very different degrees of freedom that live in the IR. And you would like to figure out what these are in terms of the UV degrees of freedom. And so 't Hooft's thought experiment was to say, well, if we imagine very weakly gauging this global symmetry that has a 't Hooft anomaly, that would, of course, be a pathological anomalous gauge symmetry. But now let me restore the sensibility of the theory as a quantum theory by adding some spectator fields. Sorry, S looks like action. Who has a favorite Greek symbol for spectator? This is the choose your own adventure part of the lecture. Sigma, okay, good, sigma. So these are not pion fields, but okay, so sigma. And we could, of course, restore the sensibility of the theory if these contributed anomaly coefficient that was opposite the physics of the contribution of the real fields. Now, the spectators only see the extremely weakly gauged global symmetry, so nothing dramatic happens to the red. So they persist down here, and they still contribute anomaly coefficient minus A. But even a phase transition in the theory is not going to undermine the anomaly-free nature of this complete story. So that tells us that whatever the infrared degrees of freedom of the actual theory are, they must still contribute an anomaly coefficient A. In other words, if we discarded the spectators, it simply says the 't Hooft anomalies match between the UV and the IR degrees of freedom. Again, 't Hooft had in mind, when he did this thought experiment, he had in mind QCD. So in my first lecture, we talked about the SU3 left cross SU3 right global symmetry of QCD, spontaneously broke into the vector. Those two SU3s have cubic 't Hooft anomalies. So there's an SU3 left cubed and an SU3 right cubed 't Hooft anomaly. And so 't Hooft was then asking the question, OK, can I match those anomalies between the UV and the IR? Now, there's two ways he could match the anomaly coefficient. One is that the IR degrees of freedom, they are rearranged, but there could still be fermions. And maybe those fermions reproduce the anomaly coefficient. In QCD, what would the fermions be in the infrared? Baryons, right. So of course, they're not going to be the mesons. The mesons are bosons, but the baryons are still fermions. And so the baryons could reproduce the 't Hooft anomaly. What's the other option? So the other thing you could do, so that just assumes the global symmetry was a good symmetry in the UV and the IR, and its 't Hooft anomalies were canceled by fermions in both cases. The other option is the symmetry could be spontaneously broken. And then it's going to be the case, actually, that the Goldstone boson will have a coupling in the theory that will compensate for the anomalous variation. So if the symmetry is spontaneously broken, there'll be Goldstones, and the Goldstone couplings will be such that they reproduce the anomaly. Okay? This is also what happens in QCD, for example, with the pion. So options, either the fermions reproduce the anomaly or the symmetry is spontaneously broken, and then Goldstones reproduce the anomaly. Just one quick sec. So now you can do the counting experiment. Given the baryons and how they transform with respect to those SU3 flavor symmetries, you can ask, do they have the right quantum numbers to reproduce the 't Hooft anomaly? And the answer is they don't. So the infrared fermions of QCD don't saturate the anomaly. And so that was very suggestive that instead what must happen is these symmetries are spontaneously broken, and it's the Goldstones that saturate the anomaly. All right, and indeed, every piece of evidence we've had since then supports this conclusion. But this is a beautiful application of this thought experiment to understand the infrared phase of QCD. Yes?
Did the baryons only acquire small map because of the rest of the term anyways, so if you didn't know about the rest of the term?
Sorry, why can't I just write down baryons that I'd say they're just composites of three fermions? Yeah. So I don't think it's necessary to have known about the West-Sumina term. OK. Good. So with regard to the standard model, we've talked about the ABJ anomalies of some of the global symmetries. What I want to emphasize is just like the SU3 left cross SU3 right global symmetries of QCD, all of these symmetries of the individual types of fermion model have 't Hooft anomalies. The most interesting ones are the 't Hooft anomalies with respect to hypercharge. So if I take any one of these factors, it has a U3 squared hypercharge 't Hooft anomaly. And you can carry out an exercise in 't Hooft anomaly matching. And that's sort of a fun exercise in a standard model at the level of its zero-form symmetries. But it becomes an extremely interesting exercise in the standard model once we think about its generalized symmetry structure. So let me say two quick things about zero-form symmetries, and then let's go to the generalized symmetries. Any questions while I'm clearing some boards? OK. I just want to invoke two more global symmetries, zero-form symmetries of the standard model, which will reappear again next lecture. So we focused all on the symmetries of the fermions, which are very nice because they have a rich anomaly structure. There is, of course, also a symmetry of the Higgs. So the symmetry of the Higgs is what's known as custodial symmetry. The idea is, let me make sure I get this right. So we know the Higgs is a doublet of SU2. If I wanted to write the Higgs field in two space, of course, it has an upper component and a lower component. We know the electromagnetic charge assignments of those are going to be the eigenvalue of the T3 generator plus the hypercharge. So there's going to be an electromagnetic charge plus one piece, a neutral piece. Of course, when the Higgs gets a vacuum expectation value down here, and the remaining three real fields become the longitudinal modes of the W's and Z's. But if I just stare at this, I can actually make a very suggestive rewriting of this by basically redundantly expressing these field variables in terms of something that transforms under a much larger symmetry. I can take the complex conjugate of the neutral piece, the charge piece, the neutral piece, and minus the complex conjugate of the charge piece. And this thing is a matrix that forms under two SU2s. Okay, so this transforms as a bidoublet under what we call an SU2 left cross SU2 right. And as is always the case, if we're being careful, the centers of these two do the same thing with respect to this object. So we can mod out by that common center. This is what's known as custodial symmetry. It's a symmetry just of the Higgs itself, in other words, of the Higgs potential. Because if I take the Higgs potential, right, we said that's mu squared mod h squared plus a quartic piece, h to the fourth. We could equivalently write this as mu squared times the trace of this bifundamental. So this is an invariant under this custodial symmetry, and similarly with the quartic. So it's just an accidental symmetry, right? Another way to put it is, there are 4 real scalars in here. I could rearrange them into a fundamental of O4, and accidentally, the SU2 weak invariant potential is also an O4 invariant potential. Okay. So it's just to say there's a larger global symmetry. Now that symmetry is broken by standard model couplings. When I turn on, for example, the hypercharge gauge coupling, the fact that so that actually gauges part of the SU2 right, so that violates the symmetry explicitly. And in fact, also the Yukawas do. It's not any one Yukawa that does it, but it's the fact that the up-type Yukawas and the down-type Yukawas are different. That also violates the symmetry. The standard model violates custodial symmetry, but again, in a controlled way that you can explore via Spurian analysis. And we go in nature and measure violations of custodial symmetry, and we see that they're very well described by the violations that we already see in the standard model parameters. And so that's another sign that any physics beyond the standard model must somehow respect the symmetry to great precision. So we'll encounter consequences of that in my third lecture. Of course, this is just a symmetry of the scalars, so there's not a very rich anomaly structure, so I just want to leave that there. And then there's one more symmetry, which in some sense amounts to taking this exercise. What have we been doing for the Spurian analysis of the standard model? We've been saying, let's take the fields of the standard model, let's imagine turning off the couplings, trying some zero-form global symmetries, and then exploring the consequences of that, okay, and treating the couplings as spurions. Well, actually, if we're really doing that, we turn off all the couplings, the gauge couplings and the Yukawa couplings and the Higgs-Cordic coupling in the standard model. Then we just have a collection of free fields. One of them is massless, right? Higgs has some mass parameter. Everyone else, in some sense, is massless. And that actually has an enormous infinite dimensional symmetry that is much larger than any of these internal symmetries we've been discussing. It's a higher spin symmetry. Okay. So infinite dimensional higher spin symmetry of the free theory. This is more familiar to people who think about CFTs, where this is also a property of massless free fields. But here it's even a symmetry of massive free fields. And you could imagine doing a Spurian analysis with respect to that infinite dimensional higher spin symmetry. We'll develop that next lecture. So right now I'll just leave that there in your heads. Hopefully that slightly your mind that really the natural end of this Spurian analysis is Spurian analysis with respect to a higher spin symmetry of the standard model. No, they're not. What I'll tell you right now, it just means there is an infinite set of even spin conserved currents. So, T mu nu is a good example. But then I could also have a 4-index symmetric tensor, which is conserved by the equations of motion, 6-index, 8-index, all the way to whatever integer you like. It is that set of conserved currents that forms the higher spin symmetry. Yeah, so I'll make that more precise on Thursday. Okay. Okay, we're not going to do all the generalized symmetries of the standard model today. We'll pick up the rest of them on Thursday because it deserves a careful treatment. But now let's get started with the generalized symmetries of the standard model. All right, so as many of you know, and as Oliver anticipated, I told you a lie at the very beginning of my first lecture, right? We said the gauge group of the standard model is SU3, SU2 across U1. We don't actually know if that is true. That is true locally, right? That is true, certainly that describes what you would say is characterized of the theory that we've measured. But that actually doesn't specify the global structure of the group. Okay. In fact, the standard model gauge group could be any one of 4 candidates. where the 4 candidates correspond to different quotients. The quotients could be with respect to a Z6, a Z3, a Z2, or basically the trivial quotient, not really actually taking a quotient. And what are these quotients? Well, you might say, oh, okay, you're taking respect to one of the centers, okay? But that's not what I'm doing. When we say we take this quotient, right, we're saying in some sense that we are gauging this discrete part of the theory so that there can be no matter representation transformed non-trivially under it. All right, that's sort of what taking this quotient means. Oh, the standard model has functions which transform under the center symmetry transformations SU3 or SU2. So this Z3 or this Z2, they're not the centers of SU3 and SU2. Rather, they are diagonal centers. And what I mean by that is the following. As we've already said when we were talking about the global symmetry structure, we could, for example, do a transformation by the SU2 left center that would multiply Q and L by -1. But we could undo that by doing a transformation by a Z2 subgroup of hypercharge. Okay? And so equivalently, what I could do is I could identify those 2 Z2 transformations, all right? And then the combination of those 2 Z2 transformations would leave Q and L invariant. And so it's appropriate to the standard model gauge group by that Z2. Similarly, I could do it with the center of SU3, or I could do both a center of SU3 and a center of SU2 and a compensating Z6 transformation in hypercharge, and that would also leave all the standard model fermions invariant. And so I could also take this quotient. Okay. So all 4 of these are candidates for the global structure of the standard model. What does that mean? Well, Todd told you at the very end of his lecture this morning, if we take the quotient of one of these gauge groups by one of these discrete subgroups, it's controlling the spectrum of line operators that are allowed in the theory. Okay? It's telling us whether or not I can have things that transform in different ways depending on which one of these quotients I take. As a phenomenologist, if I take these quotients, right, taking one of these quotients says I cannot have fields in the theory that transform non-trivially under whatever I've taken the quotient by. And so that means there can't be particles beyond the ones we know about that transform non-trivially into the symmetry. Right? As a phenomenologist, testing this is not a matter of trapping line operators in the laboratory and measuring phases. It's a matter of looking for new particles that would transform non-trivially into these, which would give you some evidence for one or the other. And finally, depending on what these quotients, we control the periodicity of the theta parameters in the standard model. Yes?
Maybe you were going to talk about this, but I was wondering if embedding the standard model in a particular grand unified group determines this way. Indeed.
So you've anticipated this was going to actually be in part of my looking beyond the standard model at the start of next lecture. But just to say, from the standard model looking up, we don't know what the global structure is. It's any one of these 4. If we knew that the standard model were embedded in a grand unified group, for example, it could be embedded in SU5 or SO10. It could be embedded in what we call Patti-Salam unification, which is SU4 cross SU2 cross SU2. Or there's something called trinification. I'll say a little bit more about these next lecture. These are all ways of unifying the standard model gauge group. And if one of these is in fact the unified structure of the standard model gauge group, then it fixes the global structure of the group. So Z6 indeed is the structure that's given to us by either SU5 or SO10. Z3 is what's given to us by Patti-Salam, and Z2 is what's given to us by trinification. Okay. I'll develop that more a little bit next lecture. But yeah, another thing that would resolve this uncertainty is getting evidence for the grand unification of the standard model. I'm putting a lot more, if I've gone through this very quickly, I apologize. Details about you can see you have the freedom to make these quotients. I'll put them in the lecture notes. But I want to develop a little bit more the generalized symmetries of the standard model before we end today. Okay. Good. What we now recognize, of course, what taking one of these quotients by, for example, maximally taking a quotient by Z6, right? That is, we would recognize, that's gauging the center of this, the diagonal center of this gauge group, okay? In modern language, we recognize center symmetries as examples of discrete one-form symmetries, because the things, as Hotat emphasized this morning, the things charged under them are the line operators of the theory. Okay. So quotient of the Z of the standard model we've taken, we end up with a one-form center symmetry, which is whatever survives the quotient. Okay, so that's one of the higher form symmetries of the standard model. Which one it is, we don't know. We don't currently have enough evidence to decide. And so again, when someone tells you that we know everything there is to know about the standard model, we don't know very basic things about the standard model. Okay, we don't know what the center symmetry of the standard model is. That's not the only one-form symmetry of the standard model. If we looked at hypercharge, okay, so as Hotat told you this morning, if I have U1 Maxwell theory, so no charged fermions and no monopoles, that has both an electric and magnetic one-form symmetry. Now, we have lots of charged fermions, right? So that breaks the electric one-form symmetry. In fact, that breaks down to the Z6 center. But the model as constructed has no monopoles. And so the magnetic one-form symmetry of hypercharge is a good one-form symmetry. Okay, so there's this interesting one-form symmetries are the up to Z6 center. But more importantly, for the remainder of my lectures, there's the magnetic one-form symmetry of U1 hypercharge, which is a good symmetry in the absence of dynamic monopoles. Okay, and so this, in fact, is a central character that will play a main role in the rest of our exploration of the generalized symmetries of the standard model. Now, these are in some sense the higher form symmetries of the standard model in the ultraviolet. You could also, again, as you go through the energy scales of the standard model to the far infrared, you could look for evidence of emergent higher form symmetries, right? So if I go, say, below 511 keV, does anyone know what emergent higher form symmetry of the standard model develops? Does anyone know what's at 511 keV? Yeah. The electron, good. So what higher form symmetry emerges below the mass of the electron? You don't have anything charged in your electromagnetism. So indeed, electromagnetism develops an emergent electric one-form symmetry below 511 keV. So the standard model has higher form symmetries both in the UV and then emergent symmetries in the infrared. Okay. Really, it does. I mean, in some sense, it has an over. So this is the Z6 center.
I mean, like QD.
It is the global symmetry of QED. QED. So there's of course a U1 gauge theory, a zero-form gauge theory, which has a one-form global symmetry, right? And so those, as Hotat described this morning, those are intimately related to each other, but not degenerate. So the fact that I have a UN gauge theory, the global symmetry corresponding to that, acting on the line operators, is the one-form symmetry. Okay, and so in the IR, there's electric one-form of UN electromagnetism. Okay, I've got 5 more minutes, but I want to start. I'm not going to finish the development of higher group symmetries, but I want to start it so that we can get somewhere interesting and then pick it up on Thursday. All right. So of course, higher form symmetries are very interesting, and thus far, as Hotat has described to you, you have higher form symmetries of differing degree, which in some sense exist in isolation from each other. It's a very interesting question, though, to ask, is there a sense in which higher form symmetries of varying degrees can mix? And indeed, they do, and they mix in the presence of anomalies, whether they be ABJ anomalies or 't Hooft anomalies. When I have an ordinary symmetry with an ABJ anomaly, typically that has an ABJ anomaly, for example, if it's with respect to a U1, and that U1 has a magnetic one-form symmetry, there's now an interweaving of the ABJ anomalous zero-form symmetry with the magnetic one-form symmetry. That's what we describe as a non-invertible symmetry. So Clay will tell you much more about that on Friday. I'm not going to go into great detail about non-invertible symmetries today. What I do want to tell you about, because it's all over the standard model, is what happens if you have a zero-form symmetry that has a 't Hooft anomaly, where it's one of these global symmetry, hypercharge 't Hooft anomalies. Because again, hypercharge has a magnetic one-form symmetry, and there will again be between zero-form 't Hooft anomalous symmetry and the hypercharge magnetic one-form symmetry that's known as a higher group. In particular, it's known as a 2 group. I should say, if you want to know everything you want to know about two-group symmetries, there's a beautiful paper by Clay, Thomas Dumitrescu, and Ken Introligator. I believe it's called Exploring Two-Group Symmetries. Clay, correct me if I got that wrong. Two-group global symmetries. It's an amazing paper. It will describe everything I'm about to tell you in much greater and more detail. So I would encourage you to go read it. And everything I know about two-group symmetries I've learned from this paper. So anything that's incorrect that I tell you in the following is on me, not on these wonderful authors. OK. Good. I'm just going to be able to give you a sense of what it is, and we'll develop it further next lecture. But the basic idea is a two-group symmetry. The nomenclature is typically you have higher form symmetries. In this situations where there are 't Hooft anomalies, they can mix with each other. You take the degree of the high form symmetry, you add one, and you append to it. So in the case of the two groups, we have a zero form global symmetry. That has a 't Hooft anomaly. And a one-form global symmetry. And if the 't Hooft anomaly, right, is one of these anomalies where it has two insertions of this zero-form symmetry current and one insertion of genuine U1 gauge. It's the magnetic one-form symmetry of that U1 gauge theory that is the one-form global symmetry that participates in this two-group. So these are the two things that will be intertwined by the presence of a 't Hooft anomaly of this form. What we'll find is, let me just give you an advertisement for the start of next lecture. What we'll find is, in the presence of these, there is a genuine symmetry of the theory, in which essentially the anomalous variation of the zero-form symmetry due to the anomaly is compensated for by symmetry transformation of the background gauge fields that we can couple to the one-form symmetry current. Okay? So that gives us a good symmetry. That's interesting on its own, but has remarkable dynamics. The symmetry is only a true symmetry when both of these ingredients are present. And in particular, because the zero-form part on its own, it's not a good symmetry, whereas the one-form part of the two-group symmetry is. It's very often the case that both of these symmetries emerge in the infrared, all right, as some degrees of freedom are integrated out. And the conclusion one can draw from this is that the one-form global symmetry always emerges at a higher or equivalent energy scale. Sense gives you an inequality of the emergence scales of these symmetries, which if you're in an EFT that has a two-group symmetry and you're looking up to the UV, this inequality has to be satisfied by whatever UV completion you can write down. Okay? And it is really interesting to ask what dynamics can satisfy this inequality. And asking this question reveals really beautiful non-perturbative phenomena. So we'll identify these two-group symmetries of the standard model and the non-perturbative phenomena they suggest at the start of my lecture on Thursday. But that's it for today. Thank you very much.